An astronaut's weight on Earth is 150 pounds. As the astronaut moves upward, Earth's gravitational pull decreases. If Earth is a sphere of radius 4,000 miles, the astronaut's weight at distance x from Earth's center is given by W of x equals 2.4 billion divided by x squared pounds. For x greater than or equal to 4,000, we need to estimate the work required to lift the astronaut 220 miles upward to the International Space Station. An astronaut's weight on Earth is 150 pounds. As the astronaut moves upward, Earth's gravitational pull decreases. If Earth is a sphere of radius 4,000 miles, the astronaut's weight at distance x from Earth's center is given by W of x equals 2.4 billion divided by x squared pounds. For x greater than or equal to 4,000, we need to estimate the work required to lift the astronaut 220 miles upward to the International Space Station. Here's Earth with radius 4,000 miles. The astronaut starts at the surface, 4,000 miles from the center. The International Space Station is 220 miles above, so 4,220 miles from Earth's center. The astronaut's weight decreases from 150 pounds at the surface to about 134.8 pounds at the ISS altitude. Let's look at the weight function W of x equals 2.4 billion over x squared. Over a large range from 4,000 to 10,000 miles, we can clearly see the curve. The function follows an inverse square law, so it decreases rapidly at first and then more slowly. Now let's zoom in on our integration interval from 4,000 to 4,220 miles. Over this small range, the curve looks almost linear, but mathematically it's still curved. This is why we need calculus to find the exact area under the curve. Work equals the integral of force with respect to distance. Since force varies with distance, we integrate the weight function from the starting position to the ending position. So work equals the integral from 4,000 to 4,220 of 2.4 billion over x squared dx. To find the antiderivative, rewrite 2.4 billion over x squared as 2.4 billion times x to the negative 2. The antiderivative is negative 2.4 billion times x to the negative 1. Or negative 2.4 billion over x. Evaluating the definite integral from 4,000 to 4,220 gives negative 2.4 billion over 4,220 minus negative 2.4 billion over 4,000. This equals 2.4 billion over 4,000 minus 2.4 billion over 4,220. 2.4 billion divided by 4,000 equals 600,000. 2.4 billion divided by 4,220 is approximately 568,720. Subtracting gives 31,280 mile-pounds. Now convert mile-pounds to foot-pounds. Using the conversion factor 5,250 feet per mile from the problem. Multiply 31,280 by 5,250. 31,280 times 5,000 is 156,400,000. 31,280 times 250 is 7,820,000. Adding gives 164,220,000 foot-pounds. or approximately 1.65 times 10 to the 8th foot-pounds. This is a huge amount of energy. It's equivalent to lifting 150 pounds over 1,000,000 feet, or about 60,000 kilojoules. Interestingly, it's slightly less than if gravity were constant all the way up, because gravity decreases with altitude. The work required to lift an astronaut 220 miles to the International Space Station is approximately 1.65 times 10 to the 8th foot-pounds. This calculation demonstrates how to handle work against a variable force using integration.